You did the examples. What did you get? Roughly 2 with both compilers? Was it? It might have been. What did you see as the numbers for, say, for Intel ICC? A factor of 4. Because that was twice as good as GCC. Yeah? Did anybody look at the single precision? Yeah? And there was the ratio.
ICC gets a factor of around 8 for between vector and no vector.
Right.
And GCC gets about 3 between vector and no vector.
Okay.
And without the vectorization, they're roughly the same.
Okay, so we had said 8 for ICC, about 3 for GCC. So that's the sort of power that you can get from simple thing with vectorization. You get a very, very nice speed up. Factor 2, factor 4, factor 8, depending on which compiler you're using and so on. Did anybody actually have a look at the value of sum and see if that differed between the vectorized and non-vectorized codes? Right. So it seems to be a problem, okay, for vectorization for the Intel compiler, in terms of that it's different number to the vectorized and the non-vectorized numbers. Single precision, this has been it's a little bit of a contrived example, as you can guess. So we're adding something which is sort of almost to a limit of single precision, but it's particularly to let you know as well that the one other difference you can sometimes get between the non-vector and vector versions, depending on the compiler, is that the x87 instructions and some other instructions used to work internally on 80 bits, whereas actually double precision is 64 bits if you're in the SSE instructions, even internally. So therefore, if there's rounding errors internally as it's doing some additions, some multiplications, they will be pushed out much more of the way if you're doing the vectorized version. If you're in the situation where that really is a problem for you, you may want to talk to a numerical analyst about the stability of your algorithms anyway. Okay, but it's the fact more that the non-vectorized version is actually being a little bit more kind to you. So in the double precision version, you shouldn't really have seen too much of a difference. Was there a real difference in GCC? No. So one of the things that you can see if you look at the assembler output of GCC is that when it actually does non-vectorized code, it's actually doing vectorized code, but it's just doing it on one element of the vector unit. So if it, for example, is 128 bits wide and you're doing a double precision number, rather than falling back to x87, it will often use 64 bits of that. That means that the rounding is there already, the same as it would be for the vector code, and you probably won't see a difference. Okay, so it's a good thing in that if you want to see repeatable results, whether you're doing vectorization or non-vectorization. Did anybody play around with vec size and iterations? Okay, what did you see happen in terms of any ratios, any change? Right. So do you know why you chose vec size of 1,000? Exactly. It was a contrived example to fit in the cache. Okay, because if it's fitting in the cache, we don't have to see any of the effects of memory bandwidth or anything else slowing things down. So we squeezed the whole application so it would the whole thing so it would fit into cache, then do enough iterations that we can time it. But by fitting into the cache, you're really just measuring the difference between vector and non-vector. Now, hopefully, if your algorithm can be worked in this way, you'll be doing a lot of work on cache to actually get yourself, so as much as possible, you do fit in cache for small parts of your code. And then the vectorization is important to you. And if you're not fitting in cache effectively, if you're throwing out all the time, then you'll slow down anyway. But David Henty is going to be talking about cache later, so I just put this in simply to show you vectorization, and I had to contrive the example. What do we actually discover from those SIMD vectorization basics? You can get some good performance improvements, and this is floating point intensive code. Depending on the instruction set or the processor you're on, you might also get integer improvements as well, where some of the SIMD units on certain processors can swap between the two. We also saw that vectorized code can give slightly different results depending on whether the instruction set on the non-vectorized version is falling back to x87 or if it's staying in the vectorized version, just shrinking it down. So it can give slightly different results. One other thing you might find as well, which was faster for the non-vector version? They were the same. Okay. You said you had Intel faster. By much? Okay. Only with double precision, not with any single precision. Okay. Just interested if there was a speed difference. That actually then can show out the compiler being good or bad. But as we said, vectorization is only one aspect of getting good performance. Effective use of the cache is also required, but we've just cheated by contriving the example, pre-assigning the thing so it's going to work nicely for the cache. So that parallelism was for free, problem solved. We don't have to do anything else. We just throw the auto-vectorizing compiler with a vectorizing flag at our code, and it's all going to work nicely. Well, clearly it's not, otherwise we wouldn't be talking to you about it. There are many times when the compiler can't, or it won't vectorize. Okay, sometimes it knows how that it could do the vectorization, but it says, well, actually, this isn't really profitable. By the time I've set up certain things to do with my vectorization, the shortness of the loop or whatever else it doesn't know about, it may say, I'm not going to do it. You can override it, depending on the compiler you're on, but how exactly, as has been mentioned earlier, how do we know what this compiler's doing? Well, most compilers, if not all of the compilers nowadays, I think, they issue you a vectorization report if you request it. So you can say, okay, what did you do? And so we're going to now do exactly that. We're going to issue vectorization reports and ask the compiler, what did you do? More importantly, in many ways, because what you're actually interested in doing is getting your code to run as fast as possible by having more of it vectorized, is to get it to tell you what it didn't do. Okay, it's often more important than what it did. Then you can go through and you would be able to concentrate on your real large application, on those parts of the code where it didn't vectorize, particularly if you ally this with some performance tool to say, and that's actually a big part of my code. Okay, so what I'd like you to do now is with exactly the same thing, just add a couple of flags. And this will then generate some vectorization reports. You'll be able to say what it can and what it can't do. And then I'd like you to add these pieces of code, depending on if you're a C or Fortran programmer, to the right place in the code, and then see what it tells you about those two little things. Okay?